থেকে হাতে পেঁচায় পেঁচায় শুরু করছে টাইনা টাইনা ওই যে কোন কামে মাগি ধরে দিকে
Hello, hello. Am I audible to everyone? Hello. Hello. Am I audible? Hello. Is this slide visible to everyone? Is this slide visible to everyone? Okay. So let's start today's lecture, which is about 8237 or 8257 DMA controller. Okay, so 8237 DMA controller. Now, actually program data transfer. What is happened in program data transfer? In program data transfer, it involves basically the moving of data from memory into the accumulator. Okay, then from accumulator it is going to the output port or output devices. Okay, so a program has to be written to transfer the data bytes from a device to the memory. And in this way, the program data transfer, so that's why it's a slow process, and this causes a problem. While transferring large amount of data. Okay, now DMA stands for direct memory access. Okay, so it is one of the ways to accomplish that high speed of data transfer, which is happening directly between the memory and the peripheral devices without the intervention of the microprocessor. And this method is often used when a large amount of data, large block of data is to be transferred. Okay, so in a DMA data transfer, uh, it is controlled using a separate DMA controller. So that DMA controller is neither a processor nor a microcontroller. It's a peripheral device which is used to perform a specific function. And what is that function? It is used to operate the DMA operation. Okay, So DMA fulfill the DMA operation, direct memory access. So using that DMA controller, we can easily implement the DMA data transfer, and the microprocessor must be disabled during that DMA data transfer. Now to start the DMA process, what happened? The microprocessor loads the external register in the DMA controller with the data file starting address. Okay, and the terminal count register with the total number of bytes that is to be transferred is to be loaded. Now the microprocessor disables the address and data buses and gives memory system control to the DMA controller. Next, the DMA controller places the sequential addresses on the microprocessor's memory bus and issues the corresponding control signals. That means read write control signals. As each byte is transferred, the terminal count register is decremented, because you have to initialize the counter below how many data bytes are there, and you need to move that data byte. So in that case, you need to operate the counter, and it will be decremented by 1 after each transfer of operation. Okay, so when the register is decremented by 1 and it reaches 0, it tells the external device that the data transfer is completed. Okay. Now, as this is a limited application. This is a limited application. A special purpose hardware controller. Special purpose hardware controller can do it very quickly, and DMA transfer takes place with speeds close to the memory cycle time. Now, once the DMA controller has finished the transferring data into or out of memory, the DMA controller gives control back to the microprocessor, and the microprocessor cannot accomplish any other function when a DMA transfer is taking place. Okay, so this is due to two reasons. First, the microprocessor memory is being used for a data transfer. It is not available to supply program instructions or receive the results of the computations. Okay. Second reason is the typical DMA process requires the microprocessor place its memory address bus and data bus in a high impedance state. Now, this high impedance state allows allows the DMA controller and the memory system to control the bus, but it prevents the microprocessor from providing any bus control, and thus the DMA controller temporarily borrows the address bus, data bus, and control bus from the microprocessor. Okay, and transfer the data bytes directly from the external peripheral device to a series of memory locations. Now, since the data transfer is done by hardware means, it is much faster than it would be if done by program instruction. Okay, so we will look into this 8237 DMA controller in details, the architecture, the features, the pin diagram, etc., and the different addressing modes. Okay, now 8237 or 8257 both are DMA controller. Okay, but according now in 8257, it is the oldest version. 8237, it is the newest version, and it has the better performance compared to 8257 because 8237 actually it is capable of transferring a byte of uh, data or bulk of data between system memory and peripheral devices in other direction. Okay, now another advantage of having this 8237 is the memory to memory transfer facility. Okay, it has the memory to memory transfer facility, and 8237 it also supports 4 independent channels, like here I have written the features one by one. So the different features are available, like it is designed to improve the data transfer rate in a system that transfer data from an IO device to the memory, or move a block of memory to an IO device. Second feature is it will also perform memory to memory data transfer, as I have told you. told earlier that memory to memory data transfer can be implemented using 8237 or fill a block of memory with data from a single location. It has different operating modes which are provided to handle single byte transfer as well as a multi-byte transfer or discontinuous data streams. Okay. It has 4 independent DMA channels through which the DMA request can be coming, and it has enable and disable features to control the individual requests, and it has the possibility for memory to memory data transfer. It has the address increment or decrement or latch operation purpose according to your requirement, because that not all time you need to increment your memory location to transfer the data bytes. Maybe you need to decrement your memory location also and transfer the data byte from one position to another position of the memory to the IO device. And the cascading mode is available so that you can connect more number of DMA channels with one DMA controller. So using 8237 DMA controller, it has 4 channels, and using these using those 4 channels, you can connect another 8237, another 4 8237 controller with these channels. So actually the cascade operation can be implemented in this 8237 DMA controller. Okay. So we will discuss about the modes also. So here is the architecture. So so here is the architecture of 8237 DMA controller. So I think some people have faced the network problem. Angona, Suman Ghosh, they are not able to join now. Okay. This is the architecture. So basically, this block diagram, architectural block diagram, Suman Ghosh. Yes. Some people have some problem with network, but I can't help it. So try to connect if you have any problem, or if you are disconnected from this, so we can come again and try to connect. Okay. So okay, so let's discuss this architecture block diagram of 8237. Basically this it contains 3 basic blocks: the timing and control block, priority encoder and priority logic block, rotating priority logic block, and different command control block. Okay. So actually these 3 blocks has been divided in this way, and internally there are lots of several registers are there through which the actual operation can be done. So basically the timing and control block, actually it generates the internal timing and external control signals. The program and command control block, this one, basically this block decodes the various commands given to the 8237 by the CPU before servicing a DMA request. It also decodes the mode control word used to select the type of the program DMA transfer. The priority encoder and a rotating priority logic block, actually it resolves the priority between the DMA channels requesting the services simultaneously, and the timing and control block derives necessary timing signals from the clock input, okay. So 8237, it houses a set of 12 types of registers. Some of these registers are present in each of the 4 channels, while the remaining are common for all the channels. Considering the multiple existence of the registers, there are 25 registers in 8237, okay. And these are the registers: the base address register, base word count register, current address register, current word count register, temporary address register, temporary word count register, status register, command register, temporary register, mode register, mask register, request register. So there are different types of registers are available in a 8237 DMA controller. So we'll discuss one by one. Okay. So basically current address register, what is it? That each of the 4 DMA channels of 8237, 8237, what happened? Okay, 4 channels first. Let me show you the 4 channels here. So this DREQ 0 to DREQ 3, these are DMA requests for the 4th channel. Like for channel 0, that is DREQ 0 and DSEK 0. One is for request channel, another is acknowledge channel. For channel 1, there is DREQ 1 signal of pin and DACK 1 pin. Okay, so in this way, 4 request channels are connected to the 4 channels, and 4 acknowledge signals has to be connected with the each channel. Okay, so here DREQ 0, DREQ 3 and DSEK 0, DSEK 3. So 4 channels has been connected in this way, through which the 4 DMA requests can be coming from the external side. Okay, now what is the base address current address register? Now each of the DMA channel of 8237 has a 16-bit current address register, that holds the current memory address. Okay, current memory address that is being accessed during the DMA transfer. The address is automatically incremented or decremented after each transfer, and the resulting address value is again stored in the current address register. Now this can be byte-wise programmed by the CPU. That is the lower byte first and the higher byte later. This may be reinitialized by an auto initialization command to its original value of after end of process signal. Okay. Second register is the current word count register. Now each channel has a 16-bit current word register that holds the number of or the count value of the data byte which will be transferred from one position to another position. Okay, the word count is decremented after each transfer of data, and the new value is again stored back to the current word register. Now when the count becomes 0 and end of process EOP signal is generated, and this can be written in successive bytes by the microprocessor and in program mode. Okay, now after the end of process signal, this may be reinitialized using auto initialize command using the command register. And next is the base address and base word count register. Now each channel has a pair of these registers. These maintain an original copy of the respective initial current address register and current word count register. Now before incrementing or decrementing, okay, that word count must be loaded inside it. Now these are automatically written along with the current registers, and this cannot be read by the CPU. The content of these register are used internally for auto initialization. Okay. Next is the command register. Next is the command register. What is this? That is the structure of command register. Each bit specific, it has specific function. Like if this bit is 0, command register bit is D0 bit is 0, then it calls the memory to memory access is disable, and if it is 1, then memory to memory access is enable. Okay, so basically command register, what is the function of this register? It's an 8-bit register, controls the complete operation of the 8237 DMA controller. Now this can be programmed by the processor and cleared by a reset operation. Okay, so these are the specific function which can be performed using this command register. Okay, so you don't have in your syllabus the function of each register. It is just for to give some knowledge about the register functions. Okay, then the next is, you don't need to remember this individual bit specification. Okay, this what, when this bit will be 0, what will be the function, or 1, you don't need to remember. Okay, you just know what is the command register, but that's all. The next is the mode register. Now each of the DMA channel has an 8-bit mode register. 8-bit mode register. Now this is written by the microprocessor in program mode. Okay, in program mode. Now bit 0 and 1, these 2 bits basically determines which of the 4 channels mode registers is to be written. Okay, the bits 2 and 3 indicates the type of DMA transfer. Now there are 3 types of DMA transfer. Okay, memory read, memory write, and verify transfer. Memory read or memory write and verify transfer. There are 3 different types of DMA transfer operation. So it needs to be selected which type of transfer operation is to be implemented according to your requirement. Now bit 4 of the mode register indicates that whether auto initialization is selected or not, while bit 5 indicates whether address increment or address decrement mode is selected. And in this way, the 6 and 7, it is for different mode selection, like demand mode, single mode, block mode, or cascade mode operation. Okay, so different modes has to be selected using this mode register, nothing else. Next is the request register. Now each channel has a request bit associated with it. Request bit, which channel is to be used to perform the DMA operation. Okay, DMA request. So each channel has a request bit associated in the request register. Now these are non-maskable. These are non-maskable. Okay, and subject to prioritization by the priority resolving network of 8237. Now each bit is set or reset under program control, or is cleared upon generation of a terminal count. What is terminal count means? When the count value is reaches to the final value, that is called the terminal count. Okay, or if any end of process signal is generated. Now this register is cleared by a reset signal, and the bit definitions are in this way. Okay. The next register is the mask register. Next register is the mask register. What is it? Sometimes it may be required to disable a DMA request of a certain channel. Now each of the 4 channel has a mask bit which can be set under program control to disable the incoming DMA request at the specific channel. Now this bit is set when corresponding channel produces an end of process signal if the channel is not programmed for auto initialization. The register is set to FF. Assume the register is set to FF after a reset operation. Okay, automatically it goes to FF. Now this disable all the DMA requests till the mask register is cleared. So if until it is cleared means all bits are 0, it will be disable all the DMA request. Next, the bit definitions are in this way. There are 2 ways. The bit numbers are one mask register is given in this position, one other is this position. Okay, so basically if individual mask bit can be used, then this format has to be given, and if simultaneous mask bits can be used, in that case this particular mask register format is to be used. Okay, the next is the status register. Status register basically it keeps the track of the DMA channels pending requests and the status of their terminal counts. Okay, the bits D0 to D3 are updated or set every time the corresponding channel reaches terminal count or an external EOP signal is generated. Now these are cleared upon a reset, and also on each status read operation it is cleared. Okay, now bits D4 to D7, if these are set, then the corresponding channel request services is to be given. Suppose channel 0 is used, at that time this bit will be 1. If channel 2 is used, or it is used to transfer the DMA request from the external input output device to the DMA controller, then this channel is to be set, this bit is to be set. So according to the requirement, the required number of channels can be set or reset using the last 4 bits of the status registers. Okay, so these are the okay, another is the temporary register. Temporary register is also there. And what is the function of this temporary register? Basically it holds the data during memory to memory data transfer. Now after the completion of the transfer operation, the last word transfer remains in the temporary register till it is cleared by the reset signal or reset operation. Okay, that is a function of temporary register. Okay, so basically these are important or the major registers inside this DMA controller. Next, so clear up to this much, I think. If you have any queries, any doubts regarding this topic until now, otherwise I will move to the next section. Okay, and when this meeting ends within 9 minutes, you have to click on the same link to continue the second session of this meeting. Okay, all of you must remember this. This meeting is ended after certain amount of time, then you need to click on the same link which I have uploaded on the Google Classroom to continue the second session.
Okay, sir.
So do you have any queries? Anyone? You can ask me. Okay, so going to the next topic, that is the pin details of the 8237 DMA controller. Indrani Hajra is unable to connect till now. Hope for the best. So so 8237 IC, it's a 40 pin IC, 40 pin IC, and it has different signal, different pins are available through which the signals are coming. Like VCC, it's a 5-volt power supply is there, VCC, this one. Ground pin is also available. Okay. So clock signal is there, clock, this one, clock signal, and internal this is the internally required clock signal for driving the internal timings required for the circuit operation. Okay, then it has the CS bar, this the pin function, it is active low chip select input of the 8237 IC. Next, it has the reset pin, reset. Now a high on this input line clears the command status, request and temporary registers, and it also clears the internal first and last flip-flop and sets the mask register. Actually the 8237 remains stuck to reset till the reset pin is high. Okay. The next is the ready pin. The active high input is used to match the read or write speed of 8237 with slow memories or IO devices. Those are connected with this 8237 DMA controller system. Next is the HLDA, hold acknowledge, hold acknowledge. This active high input signal is to be connected with HLDA pin of the CPU to indicate to the 8237 that the CPU has released the control of the buses, okay, as a response to a bus request. Next is the DREQ. This DREQ 0 to DREQ 3 DMA request inputs. Now these inputs basically are used by the individual channels request inputs driven by the peripheral devices to request a DMA service. Okay, DREQ 0, it has the highest priority, while DREQ 3 it has the lowest priority. The priorities of the DREQ lines is programmable. Okay, it based on the programming requirement. Now after reset, what happened, these lines becomes active high, and the active level of these lines is also programmable. Okay, the DREQ this DMA request must be maintained high until the corresponding DACK pin goes high. Next is this DB0 to DB7. These are the bidirectional lines used for data transfer, that is to or from IO or memory devices. Okay, during IO read, what happens, the contents of the address register, status register, temporary registers, or word count registers are sent to the CPU over these lines. Okay, and during IO write, the CPU sends the data to any of the
registers from the address register, from the status register, from the temporary register, or from the word count registers. Okay. Now in memory to memory operation, this the 8237 fetches the data from the memory using these lines during read memory transfer cycle, and also the data is transferred to the memory on these 8 lines during write memory transfer cycle. Okay. The next is the IO read and IO write. Basically, IO read, that is a bidirectional active low line. In there are 2 cycle in DMA operation. One is the ideal cycle, another is the active cycle. Ideal cycle, active cycle. In ideal cycle or in passive mode, this is an input control signal used by the CPU to read its registers. Okay, I read. And what happened in the active cycle? It is an output control signal used by the 8237 to access data from a peripheral. In the same way, for IO write operation, in ideal cycle, it is an input control signal used by the CPU to load information into the 8237. And in the active mode, in the active cycle, it is an output control signal used by the 8237 to transfer data to the peripherals. Okay. A0 to A3 and A4 to A7. A0 to A3, basically these 4 least significant address lines are bidirectional 3-state signals. In ideal cycle, they are inputs and are used by the processor to address the control registers to be read or written. And in case of active cycle, they provide the lowest 4 bits of the output addresses generated by the 8237 DMA controller. And A4 to A7, these 4 most significant address lines activated only during the DMA service to generate the respective address bits. HRQ, this hold request line, it's an output pin used to request the control of the system bus from CPU, and if the corresponding mask bit is not set, every bit of the DREQ to 8237 will issue a hold request signal, HRQ hold request signal to the CPU. Now this is connected either to hold pin of the minimum mode of 8086 microprocessor or to RQ bar or GT bar, request grant bar, which is in maximum mode pin of the 8086 microprocessor. Okay. Now DSCK 0 to DSCK 3, DMA acknowledge. This DMA acknowledge actually it output pins are used to indicate the individual peripherals that it has been granted a DMA cycle by the processor in coordination with 8237. After reset, these are active low but may be programmed as required by the end user. Okay. AEN, this is address enable. This is active high output enable pin, 8-bit latch that drives the upper 8-bit address bus. The address enable pin is used to disable other bus drivers during DMA transfer. Okay. And ADS-TV, address